Well, students, in the third chapter on numerical linear algebra, so far we have covered linear systems, and now we will pass on to eigenvalue problems, where we will try to devise a method called power method to compute the dominant eigenvalue of a given matrix. Let us first motivate why at all we need a method to obtain eigenvalues, because eigenvalues come as a root of a polynomial, right? Anyway, in the next chapter, we are going to learn how to approximate roots of any nonlinear equation. If that is so, why we are spending time on building methods for eigenvalue problems as a separate topic? Let us try to motivate this. For that, let us quickly recall what is eigenvalue of a matrix. You are given a matrix A, which is a n cross n matrix with real entries. The eigenvalues of A are defined as the root of the equation determinant of lambda into identity matrix minus A equal to 0. Right? Note that this is a polynomial equation in lambda of degree n, right? And it is called characteristic polynomial of the matrix A. Generally, the roots of these polynomials need not be real. They can be complex numbers. It is also known that for every matrix, we have n eigenvalues. Some may be repeated according to their algebraic multiplicity. Now, in all this, what we found is that to obtain the eigenvalues of a matrix, we have to solve this characteristic polynomial equation. Well, if n is equal to 2, this equation is a quadratic polynomial equation, which we know how to find roots because we have explicit formula. If n is equal to 3, somehow we can manage to get the roots, but from n is equal to 4 onwards, it is very difficult to find roots of these polynomials through a nice formula, right? We can of course find through some approximation methods, but in general it is not that easy if your matrix is 4 cross 4 matrix or of higher dimension. Therefore, a numerical approximation method is very important for us to compute eigenvalues of a given matrix. Well, as I told, we may go for any nonlinear solvers, which we will be developing in the next chapter, like Newton-Raphson method or secant method or whatever, that can give us root of any nonlinear equation. In particular, it can give root of a characteristic equation of a matrix. One obvious way of approximating an eigenvalue of a matrix, as I told previously, is to first get the polynomial equation for lambda, that is the characteristic polynomial, and then use some nonlinear solvers like Newton-Raphson method or secant method or whatever it is. We will be talking about this in the next chapter. You can use one of those nonlinear solvers to get a root of the polynomial, that is the characteristic polynomial, right? But this is not an efficient way of computing eigenvalues because of two reasons. One is, you are given a matrix. To obtain the characteristic equation itself is very difficult, right? Especially when the matrix A is a large matrix, in the sense that its dimension is very large. Secondly, if you make even small error in building this polynomial, like when you try to build this polynomial on a computer, you cannot avoid having floating point errors, right? So therefore, if you make even a small error in the characteristic polynomial, then the root of this polynomial may be entirely different from what you want as eigenvalue of your matrix. Of course, the second difficulty is more serious, and it is very well known also that very close by polynomials may have entirely different roots. Let us just give an example for this. Consider the polynomial f of x equal to x minus 1, x minus 2 into and so on till x minus 10. Let us call this as f of x. And now we can clearly see from the way this f of x is defined, the roots of the polynomial equation are 1, 2, 3 up to 10, right? And all are distinct roots. Now what we will do is we will define another polynomial, capital F of x, where only the leading term coefficient is slightly perturbed. Say 1% we are perturbing, right? What we are doing is we are keeping f of x as it is, and then we are taking x to the power of 10 and multiply it by 0.01. Therefore, your leading term, that is x to the power of 10, will have the coefficient as 1.01 x to the power of 10, plus the other terms are just as they are in f of x, right? So only here we have a slight error. Now let us see how the root of the polynomial equation capital F of x equal to 0 looks like. In fact, they all lie in the interval 1 to 3.5, whereas small f of x equal to 0, roots are lying in the interval 1 to 10, right? In fact, they are just integers. Let us in fact see this graphically. Here, the blue solid line indicates the graph of the function f of x, where this is the x-axis and the y-axis is precisely y equal to f of x, right? Now you can see that the roots are 1, 2, 3 and so on till 10, right? This is the largest root of your polynomial equation f of x equal to 0. Okay, so all these are these points and so on. Now let us see how the capital F of x graph look like. Capital F of x graph is represented by red solid line, and the blue solid line is as usual the graph of the function small f of x. And you can see that your capital F of x graph just grows off and it has roots up to here. The real roots are stopping here, and the maximum value of the real root is given by 3.3980 and so on. This is approximately. And now you can see that it may be having all other roots as complex roots, or it may have other real roots. But what is very important to see here is that the capital F of x has no root other than these roots in the interval 1 to 10. This is unlike the polynomial equation small f of x, right? So you just perturbed your polynomial small f of x by just 1% in one of the coefficients only. Just imagine if you have error in all other coefficients, then it is much more worse maybe. But what we are seeing here is just having one coefficient small error lead to drastically different set of roots. Therefore, going for characteristic polynomial building and then finding the root is not an efficient way, and also accuracy wise it may not be good at all. Now the next question is then how to obtain eigenvalues without going to the roots of the characteristic polynomial of the matrix. There's one more way which is used in computing the dominant eigenvalue of a matrix, and that method is called power method. As I told, it just computes the dominant eigenvalue of the matrix. Let us first see what is meant by dominant eigenvalue. Let A be an n cross n matrix, and let mu1, mu2 up to mu be the eigenvalues of the matrix A. Some may be repeated as per the algebraic multiplicities. First, let us arrange these eigenvalues in an order like this and rename them as lambda 1, lambda 2 up to lambda n after rearranging them, then lambda 1 is called the dominant eigenvalue of the matrix A. Let us give two examples now. There are situations in which a matrix may have a unique dominant eigenvalue, and sometimes the matrix may have distinct eigenvalues, but dominant eigenvalue may not be unique. To illustrate this, we will consider the following examples. Let's start with the example 1, where the matrix A is given like this. With simple calculation, you can see that the eigenvalues are 1, -1 and -2. And from here, you can see that -2 is the dominant eigenvalue. And of course, you can also see that it is unique here. Let us take another example where we take a matrix B like this. And if you compute the eigenvalues of the matrix B, you can see that they are 1, -2 and 2. Now you see, we have to arrange them in this way. Lambda 1 greater than or equal to lambda 2, right? Greater than or equal to lambda 3. And then you have to take the one which has the largest absolute value is what is called the dominant eigenvalue for us. Here you can see that there are two eigenvalues which will contribute to be the dominant eigenvalues, right? Therefore, for the matrix B, the dominant eigenvalue is not unique. However, it has three distinct eigenvalues. So this is an important point that one has to note. This is because the power method can be used to compute dominant eigenvalues and the corresponding eigenvectors of a matrix, provided the eigenvalue, that is the dominant eigenvalue, is unique. Okay, so this is very important. If the dominant eigenvalue is not unique, then power method may not converge. So if you go back to our above examples, we can see that we may be able to use the power method successfully for matrix A, but not for the matrix B. Let us now derive the power method and prove its convergence result. Let us now derive the power method. First, let us collect all the properties that are needed to derive the power method. First, assume that the n cross n matrix A has real eigenvalues lambda 1, lambda 2 up to lambda n. The first property that we need is that the dominant eigenvalue should be unique. That is what we have mentioned here by writing this strict inequality. And the second property that we need to build the power method is that the corresponding eigenvectors denoted by v1, v2 up to vn are real and forms a basis for Rn. What does it mean? It means that you give me any vector in Rn, I can write that vector as the linear combination of vi's, right? So these two conditions are needed for us to derive the power method. The power method consists of building two sequences. One sequence is expected to converge to the dominant eigenvalue of the matrix, and another sequence is a sequence of vectors which is expected to converge to a corresponding eigenvector of the dominant eigenvalue. Let us see how to construct these two sequences. For that, we basically have to take this representation of any vector and pre-multiply that vector by A on both sides. Now recall, we have V is equal to C1 B1 dash 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 up to Cn Bn, right? So when you multiply by A on both sides, you will be having this equation. Now, since V1 is the eigenvector corresponding to lambda 1. This can be written as lambda 1 v1 and so on. And this can be written as lambda n Vn, right? So that is what we have written here. Once you have this representation for AV, then you can take lambda 1 outside as a common factor and write the right-hand side expression like this. And in this, you again go to multiply A on both sides. Again, you take A inside, and that can be written as lambda 1 v1. And similarly, here you will have lambda 2 v2 and so on. Finally, you will have here lambda n vn, right? And again, in that, you take lambda 1 outside and you have c1 v1 plus c2 lambda 2 divided by lambda 1 square now, because you have taken lambda 1 outside, and similarly the other terms. Again, you pre-multiply by A, therefore you have A cube here. You will have one more lambda 1 v1 coming here when you multiply this by A, and similarly the other terms, when you multiply this by A, you have lambda 2 v2 and so on. Again, you remove lambda 1 outside and make it as cube, and everything will become cube here. Like that, you keep on going. At any stage, say k can be 1, 2, and so on. It goes on like that. At every stage, when you multiply by A, you have A to the power of k, and that will lead to lambda 1 to the power of k times c1 v1 and the other terms with k as the power, right? So let us see what we can do with this expression. Up to here, it's very elementary. We started with our representation of any vector v as the linear combination of the eigenvectors, because we assumed that the eigenvectors form a basis for Rn. And then we kept on pre-multiplying A on both sides. And every time when we multiply, we remove lambda 1 outside the expression on the right hand side, and we finally get at the kth level, you have this expression. So this is what we got. Now you see lambda 1 is strictly greater than the other eigenvalues, right? Therefore, each expression in the bracket, that is lambda 2 by lambda 1, is strictly less than 1, right? Similarly, lambda 3 by lambda 1 is strictly less than 1, and so on till lambda n by lambda 1 is strictly less than 1. So why we are doing that? Clearly, when you take k tending to infinity, all these terms goes to 0, and you will be only left out with this term. That is the idea. Let us see how it goes. So since we have assumed that lambda 1 is strictly greater than the other eigenvalues in their absolute value, you can see that lambda k by lambda 1 is less than 1 for k equal to 2, 3, and so on up to n. And using this fact, we can see that lambda k by v, I am taking this to the other side and making it to in the denominator. And thereby, you have this is equal to this entire expression, right? And that expression converges to only the first term, because all these terms will go to 0 as k tends to infinity, right? Therefore, what remains is c1 v1, and this entire expression goes to c1 v1 as k tends to infinity. So that is the interesting part here. Now for c1 not equal to 0, the right hand side of the above equation, that is this one, is a scalar multiple of the eigenvector v1, which is corresponding to the dominant eigenvalue, right? So that's a very interesting part too. Therefore, we see that this sequence is kind of converging to a scalar multiple of an eigenvector of lambda 1. Now, what you do is you take this term. What is this? You take a k plus 1 b, which you obtained at the k plus 1th step. You take any one component of this vector. Doesn't matter which component. You take any one component of this vector, divide it by a k v, the previous steps vector, and take the same component I. What will happen? Clearly, you have akv is this one divided by this one. What is the numerator? Numerator is lambda to the power of k plus 1 into c1 v1 plus and so on, plus lambda n by lambda 1 to the power of k vn. Remember, these are vectors, but you are only taking the ith component of that vector, right? Therefore, that is the expression you are getting here. And now as k tends to infinity, all these terms goes to 0, right? All these terms goes to 0. Similarly here, all these terms goes to 0. And what remains is c1 v1 ith component. Similarly in the numerator also, c1 v1 ith component, they both will get cancelled. And you have one lambda k here in the denominator and lambda k plus 1 in the numerator, and that will contribute to lambda 1 here. And this is lambda 1 here. So you have this, and that clearly shows that you have another sequence, which is a sequence of real numbers. This is a sequence of vectors, right? And this is a sequence of real numbers, and that is converging to the eigenvalue lambda 1. And this sequence of vectors is converging to an eigenvector of lambda 1. That is what we have seen from these calculations. So this is the basic idea of power method. Let us precisely write the formulas now in the form of an iterative sequence. So we have two sequences, as I told. One is a sequence of real numbers and another is a sequence of vectors. And we have to construct these two sequences using the idea that we developed previously, that is this idea. If we develop such sequences, then there is a scope that this sequence mu k will converge to lambda 1, and this sequence xk converges to an eigenvector of lambda 1, right? So that's the idea. Remember, this cannot be taken directly because we have taken this vector to be some unknown vector, but that doesn't matter. What you can do is you can start with any vector that you like, just like how we used to do for the iterative methods for linear systems. Like for instance, in Jacobi and Gauss-Seidel, we started with any initial guess, and then we eventually generated a sequence of vectors. Similarly here also, you can start with any given vector and then start generating the sequences. So let us give these two sequences more precisely. You choose a vector x0 and multiply a with x0 and call this as y1. Now what you do is with y1, you choose that component of y1. You see, you finally have to choose one component here, right? That component, instead of choosing randomly, you do it in a particular way. What is that particular way? you choose that component for which this vector y attains its maximum norm. Recall, the maximum norm is nothing but the maximum of the absolute values of the components of the vector, right? So what you will do is you will take maximum over all I is equal to 1 to n, yi you will take and see who attains this maximum at the first time, right? Say for instance, your y vector is 1, 2 and minus 2, then y attained its maximum at the second component and third component. So you can take the second component as your I, that is I equal to 2. So once you take that, then define x1. Remember, you started with x0. Now you are defining x1 as y1 divided by mu. That is equivalent to this, you see. Okay. And next time when you go to take the maximum, you again will do the same procedure. You define y2 as a x1 and then mu2 as yi of 2, where I is the minimum value at which the maximum norm is achieved for the vector y2, and then define x2 as y2 divided by that mu2, right? So you keep on doing that, and in that way you have two sequences. One is sequence mu k, which is a sequence of real numbers, and another sequence xk, which is the sequence of vectors.